Thank you very much, Kelly. Um, Thanks for the presentation. My name is Thomas Hudson. I'm an applications engineer here at MPS. And today I want to talk to you about constant on-time control for powering FPGAs and other high current loads that require high current fast transient power supplies. So just so we have a bit of an overview of what we're going to be seeing, we're going to start off discussing a more commonly known control method, which is peak current mode control. And then we're going to look at why constant on time has been adopted for these sorts of power supplies, for these sorts of applications such as FPGAs and ASICs, and going over the advantages that constant on time presents and also the challenges that we need to get over. Then I'm going to dive a bit deeper into the way that MPS implements our constant on time in these in our power modules designed for supplying FPGAs, and a bit into what we have to offer and how we can help ease the design process. So without further ado, we can start with, as I said, a more commonly known way of controlling power supplies, which is current mode control. In this case, we're going to be talking about peak current mode control. So as I'm sure many of you are familiar with this control method, where we have two control loops. The first one is the voltage loop, which is what we call also the slow loop. This senses the output voltage. We use a resistive divider, and it goes through this linear compensator that outputs this comp signal that you can see here in blue. The second loop that we use in this form of control is the current loop, or the fast loop. Here we're sensing the inductor current, and we use these two signals to generate the PWM signal that we then send to the drivers that control the switches in our buck converter. So inside the PWM generator, we have a comparator and we have a clock signal. The clock signal indicates when the drivers should close this high side switch. In this case, I've kept it simple. So we just have control over this high side switch. So the clock is going to indicate when the drive signal goes high. And then by using the comparator and this PWM latch, once the inductor current reaches the same value as this compensator signal that we've gotten from the voltage loop, the latch is reset, and it's the signal for the PWM signal to go low. This is how we then generate this PWM that's going to be able to modify the duty cycle when we have changes in the required output voltage or the required load current that we need to supply to the output. This method, as I said, is very commonly used. It's very often part of all the syllabuses in college and university, and it's something that's been widely used in the industry as a way of controlling DC-DC power supplies. However, as the loads that we try to power evolve, so do the control methods. And in this case, with the advent of or the increase in power requirements from FPGAs and ASICs, we need to find faster control loops or faster control methods. This is because, of course, FPGAs have large dynamic current variations depending on the circuit that we implement. In the FPGA, we can have very sudden current shifts, and the additional requirement here is we need to deliver the energy to our load as quickly as possible without seeing a drop in the output voltage. So if we reduce this to the basic requirement that we need a faster transient response, then we need to analyze where we can increase our response speed. So first of all, we see two basic things that we can resolve. One is we can improve our response by not having to wait between one clock signal and the other clock period to deliver the energy. This is going to limit how much energy we can deliver to the load instantaneously. Secondly, we have a delay in our control, and the main culprit that we can look at is what we already called the slow loop, the voltage loop. This delay is mainly due to the linear compensation that we have in this loop. So if we want to increase speed, then the first thing that we can do is we can just scrap our compensator and directly connect the output voltage sensing to our comparator. In this way, we can eliminate this delay. And in the second aspect, I'll go into that later on, but of course, without the compensator, we don't have this compensation signal that we were seeing here. So we substitute this for a fixed voltage reference. The second aspect that we can shorten the response time with is by eliminating the clock signal. So instead of using the clock signal and into the latch, we use a one-shot timer. The one-shot timer delivers a fixed pulse width, so a fixed on time, thus the name constant on time control. And what we're changing here is not so much the width of our pulse, but we're shortening or lengthening the total switching period. So we're changing the frequency. This means that in steady state, we can have a more or less steady switching frequency. Once the voltage begins to drop and drops below our reference, then we deliver an additional pulse of so allowing energy to flow from the input to the output or to the load, and increasing the output voltage again until it reaches the reference. However, when we see a sudden rise in the output current, then instead of having to wait for the clock, we can instantaneously deliver as many pulses as necessary in order to supply that energy through the output capacitor, and therefore maintain this output voltage high and be able to meet the requirements of steady voltage delivery to targets such as the FPGA. So this would be our general view of the constant on-time control. The advantages of the constant on-time control, first one is evident. It's the main purpose. We want to be able to increase our low transient performance. So we want to make it as fast as possible and reducing the droop in the output voltage as much as possible. The additional advantages of using constant on time is that we simplify the architecture due to the elimination of the compensator. And we also it also allows us to seamlessly transition between light load operation and heavy load operation, as well as not requiring an internal oscillator due to the lack of a clock signal. I'll go into these advantages more in depth in the following slides, but I also want to mention that changing to constant on time also comes with its own set of challenges that we must address. First of which is that the feedback voltage is what we're using to as the input signal to our control, and therefore we require a certain periodicity in the feedback voltage signal. I'll go into more detail on this later on, but it's going to be dependent somehow on the ESR of our output capacitor. Secondly, the switching frequency is therefore going to depend not only on the output load current, it's also going to depend on the ratio between the input and output voltages. And therefore, this can mean that we can have variations in our switching frequency dependent on, for example, variations in the input voltage. This can be problematic because we as engineers, we want to know exactly what frequencies are present in our circuit, and that's already hard enough to do when we have a fixed switching frequency. So variations in the switching frequency is something that we want to minimize. So going back to the advantages, as I said before, when we have this change in the load, instead of having to wait for our clock signal and waiting on the delay from our error amplifier, we can immediately start delivering pulses with constant on time, and therefore try and deliver the required energy from the input to the output as fast as possible, without relying so much on the capacitors discharging to deliver this energy instantaneously. This allows us to deliver sudden high current steps with reduced drops in the output voltage. In a real example, we took two equivalent converters, one using peak current mode and the other using constant on-time control. And we used them in the same operating conditions, so 12 volts in, 3.3 out, and did a 3.5 amp load step, which in many cases is pretty small to what we're seeing, for example, in the core rails for some FPGAs. We use the same inductors and the same output capacitors, and just in this small load step, as I said, we can already see a very big difference between the peak current mode and the constant on-time transient performance. With the peak current mode, we were achieving about an 8% variation from our reference voltage, our desired output, and during the transitions in the load current, we saw a peak-to-peak difference of 0.5 volts, more or less, so an 8% variation. When we switch to the constant on-time, the fact that we don't have to wait for this clock signal means that we can deliver the energy faster, so this energy doesn't have to come so much from the capacitors, so we reduce this peak-to-peak voltage difference down to 2.5%. This value is pretty important because when working with FPGAs, very often there's very strict stability requirements, especially in core power rails. So for example, this is from our reference design. I'll talk more about reference designs later on in the presentation. But for example, the core power rail here is a 1 volt 20 amp rail. And in this case, we can see very easily, we can see variations from, say, 2 or 3 amps up to 16, 17, very sharp, very high DVDTs, DIDTs in this load current changes. And the requirement in the stabilities is often around 3%. So at 1 volt, this means that we can only vary about 30 millivolts when doing this load step. In this reference design, for example, we use the 369525 power module. MPS power modules, just as a quick introduction or reminder, in our power modules, we integrate not only the converter, so the power FETs and the control, we also integrate the inductor and some of the other passive components in the circuit into a single package. So with these 3 modules, we're delivering the main rails required for this FPGA, and the 369525 can deliver up to 20 amps of continuous output current, as well as supporting digital communication for both for monitoring and also for programming different parameters such as the output voltage or the switching frequency, and using, as I said, constant on-time control for delivering these very fast transients. Second advantage that I want to touch on for constant on-time is that the fact that we're not requiring a compensator, or we're eliminating the compensator from the compensation loop, means that we are eliminating essentially the delay that comes from the error amplifier, as well as the delay that comes from our RS latch that we're using for the PWM. One of the reasons why COT is so fast is precisely because of the elimination of this of these elements in the compensation. But this also reduces the time that we spend designing our control loop. It simplifies the design because I'm sure many of you are familiar with the time it takes when you're testing and simulating, or if you're then testing out on the board, modifying and testing different values for these resistors and capacitors is a very time-consuming process. So in constant on-time control, we only have our high-speed comparator, and that directly goes into generating the PWM signal. Third advantage I wanted to mention is the transition from light load to heavy load. When we use more traditional control methods, such as current mode control, when we operate in light load conditions, the frequency can be greatly reduced. So we try to increase our efficiency by using alternative control methods when operating at light load. For example, at MPS, we have our advanced asynchronous mode, which basically implements pulse skipping. With a constant on time, as I said, the pulse is only activated once the output voltage drops below the reference. This means that as the current increases, the flow from operating in light load to heavy load operation doesn't require a change in the way that we control the circuit, which can occur in current mode control. This then generates in certain operating points, it can cause a droop in efficiency due to the converter moving between both these control methods. Whereas here, as you can see, it's a very smooth progression in the efficiency. An example of this that's implemented in our products is in the MPM 3804, 1424, and 34. These are our low current modules designed for some lower current power rails in FPGAs. And these come in very small packages. For example, our MPM 3834 is a 3 amp power module in just a 2.5 by 2.5 package. As I said before, we integrate both the control, the power stage, and the inductor in one single package. All we need in this case is our output voltage divider, our output capacitors, and input capacitors. And as you can see, we maintain a high efficiency very stably through very light loads up to the whole current range. The next step after talking about the advantages is, of course, we need to mention the challenges of using constant on-time control. So the first one that I wanted to mention is the variability of the frequency. So as I said before, not only are we going to depend on the output current to set the frequency. So when we increase the current, the voltage drops faster. Therefore, we need to deliver these bursts of energy at a higher frequency. It's also going to depend on the operating point or the conversion ratio between the input voltage and the output voltage. This means that even if we have a steady load current, if we have variations in the input voltage, this can make the steady state frequency vary in a certain margin. This can be problematic for certain applications. As I said before, we want to have our switching frequency as stable as possible, at least in steady state. We won't be able to avoid variations due to the load current, but we want to at least be certain that when we're operating in steady state, we have a good idea of what that switching frequency is. So the way that we have resolved this is using adaptive constant on-time control and adding into the one-shot timer the input and output voltages so that we can therefore maintain steady switching frequency during this steady state. So even if there's variations or noise in the input voltage, this doesn't have an effect on the switching frequency of the converter. This allows us to have a better idea or be more at ease of what frequencies we will be seeing in steady state. The second challenge, and this is the one that we see most when working with constant on-time converters, is that the the stability is largely dependent on the ESR. So as I said before, we are using the output ripple as the main source for our, or as the main input for our control loop. So we are dependent on the shape of this ripple in the stability of our control. So let's take a look at what two components make up this output voltage ripple. First, we have the ESR current. ESR, or the equivalent series resistor of the capacitor, is a parasitic element which is present in all capacitors. The only difference is in the type of certain types of capacitors tend to have more ESR and others have smaller ones. So as current flows through this ESR as the capacitor is being charged and discharged, this generates a voltage drop, and we can see the shape of this voltage in green here in this graph. The good thing about this ESR ripple is that because it comes from the inductor current, we can see that the shape that it has is very similar to the one that we saw when we were sensing the inductor current in our current mode control. So we can see that the peak of our ESR ripple occurs at the time where we switch off the PWM signal. So as the inductor charges, this voltage increases. However, the second element is the capacitor voltage itself. And the problem with this is that, as you can see here in the blue, the peak of the capacitor ripple occurs much after the duty cycle or the on time is finished. So by superposing both of these ripples, we get the total ripple, which has not usually or ideally a shape much like this one. So the problem here is if we have an ESR, so if we have a ripple that's dominated by the ESR ripple, then our ripple voltage will look like this, which periodic. It allows us to have a very stable control and very fast transient response. However, if our ESR is very small because we're using, say, MLCC capacitors, which is generally what we mainly use as our output bulk capacitance, or what we aim to use because they're also the most cost-efficient way of implementing this output capacitor, they have very small ESRs, and therefore we run the risk that the dominating component of our output voltage ripple is not the ESR, but the capacitor voltage. This can lead the control loop to enter subharmonic oscillation, and much in the way that we can find subharmonic oscillation in other forms of control, such as current mode control. This can lead to unstable operation in our control loop and therefore not being able to deliver a well-regulated output voltage. So this poses a big problem to resolve when wanting to implement constant on time. Luckily, there's several solutions. One, which is pretty obvious, is using output capacitors with high ESR. This is, as I said, a pretty obvious solution, but also problematic because it means that we have a reduction in the efficiency. It also, using high ESR capacitors is often take up much more space. And as I said before, we want to be using MLCCs as much as possible in our designs. So the second option we have is for resolving the subharmonic oscillation in a pretty similar way that we resolve it in current mode control, which is adding a ramp voltage to our feedback signal. This will ensure that we have periodicity in our control signal, and therefore we'll be able to avoid entering subharmonic oscillation. However, adding this ramp voltage can be a struggle. So what we do instead, and this is especially implementable in our modules, is we add this RC circuit in parallel to our inductor, which generates this ramp voltage by, and therefore we have this large signal entering our control loop, and therefore regardless of the the ratio between the components of the output voltage, the ESR, and the capacitor ripple, we will always have a tendency towards this slope voltage, which has the same shape as our ESR ripple. This will mean that regardless of the capacitors that we use and the ESR of these capacitors, we are much more certain that we will be able to have a proper periodic shape of the total output voltage ripple, and therefore guarantee stable operation of our converter. So into an implementation of one of these, I wanted to talk a bit about the 3695-100. This is our 100 amp power modules, as you can see here on the top right. Comes in a BGA package, which is 15 millimeters by 50 millimeters by 30 millimeters. So this integrates 4 phases inside. So it uses a multi-phase operation in order to deliver these 100 amps. So as I said before, we integrate all 4 phases, the control and the power conversion and the inductor, into this one package. And this these 4 phases inside our module, the modules can also be paralleled to deliver up to 800 amps in a multi-phase operation. This I wanted to touch on because even though, as I said before, the frequency is going to depend on the load current, we can still get the advantages of operating in multi-phase, regardless of operating in constant on time. So we can further get improvements on our transient performance. And the fact that we can deliver the required energy to our loads as fast as we can using constant on time means that we are less dependent on these output capacitors to deliver this instantaneous energy to our load. This means that we reduce the required capacitance of our output capacitor, and therefore can save a lot of board space and a lot of BOM cost by using constant on time and using these constant on time multi-phase modules. The other aspect that I wanted to show is that they also require very few external components, and the layout is also very simple. So we further reduce time in our design cycle. And also when doing our prototyping and doing our designs, many of our modules, especially these high current modules, come with digital programmability. This allows us to modify parameters very easily, and it will allow us to very quickly be able to trim and modify parameters such as the output voltage or the switching frequency or certain protections, and as well as being able to monitor the output current, the output voltage, and the temperature of our modules, which is very important in critical rails such as the core power rails of an FPGA. So just to give a bit more of information on this auto interleaving constant on time, as I said before, we can put up to 8 of these modules in parallel. This evaluation board is our 800 amp evaluation board, which is available on the website for ordering. We also have a 400 amp version and a 200 amp version and a single IC version as well. These are all available. But if many of you have worked, I imagine, with multi-phase converters in the past, so you know that the advantages of using multi-phase converters is that we can deliver energy much faster to our load, and we can also reduce the output ripple significantly. However, it also entails certain added complexity to our design, being first of all making sure that we are properly operating in multi-phase, distributing the phase differences equally amongst the different converters, as well as balancing the output current. Because, for example, if we want to deliver 200 amps to the output and we're working with just 2 of these modules, we want to make sure that each one of these is delivering 100 amps and not one's delivering 50 and the other 150, because that is going to lead us to potentially to failure of the device. So that's why MPS modules have active current balancing. So we use the current monitoring that you can also see via the I²C to make sure that all the modules are delivering the same amount of current. Second aspect that I wanted to explain is we also aim to simplify the use of multi-phase operation by using the auto interleaving. The auto interleaving works by automatically detecting a master module and, as I said, up to 7 slave modules. But very simply, we have 3 pins: the take pin, the pass pin, and the run pin. And then if we connect the take pin to VCC, for example, this automatically selects this module as the master, which is then going to deliver the appropriate PWM signals using the pass or the run pins to the next module. And therefore, then by knowing how many modules are connected in parallel, we can equally divide the phase shifts amongst the modules and make sure they are all working in balance both in current and in phase. And we have so we have these 3 pins: the pass, the run, and the take. And this is because it also allows us to connect the phases inside the module in different ways. Basically, we have 2 options. If we use the run connected to the take pin, we can have basically these 2 modules operating in parallel. So there's only 4 phases in both of these. So at any given time, we're using 2 converters in the same in phase. This allows us to deliver more current to the load, so we will be able to deliver higher peak currents and therefore increase our transient speed. However, it is going to also have a slightly larger ripple than option 2 using the pass and the take pin, because here we're using effectively an 8-phase operation. So the difference between the phases is only 45 degrees. This is going to mean that at any given moment, we only have 1 converter operating, but it will allow us to have a smaller ripple. So it all depends on our requirements and our system requirements. When we connect up to 8 modules, for example, in the 3695, excuse me, we can use a combination of either option 1 and option 2. So we can have a combination of these when we're using in 4 phases or in 8 phases. The other element that I wanted to mention of the 3695, which I touched on before, is the ability to program very easily using our software VirtualBench Pro 4. Most of our parts that have digital programmability are available on this software. And this allows us to very easily both monitor the parameters such as the output voltage or the output current or the temperature. And also it allows us to modify parameters on the fly, such as basic parameters. We can see the output voltage, we can modify the switching frequency, we can modify, well, the switching frequency, we can modify the minimum on time, the minimum off time, and then we can also switch some phases on and off and enable and disable these converters via PM bus or I²C. And in some of our other modules, more advanced modules, there are advanced parameters that we can modify, such as those that we use or those that we've inherited from data center or telecom applications, which are already used to operating in these very high current, very fast load step applications, such as active voltage positioning or load line configuration, or modifying parameters for high-speed proprietary communication protocols such as Smart VID or AVS bus. And we can also modify protections, and we can modify current monitoring, so we can meet the different requirements from different manufacturers on how we protect both the FPGA and the power supply from potential issues or overcurrents or general current monitoring to increase efficiency. And we can also modify some aspects of the PMW control So the PWM control, the amount of phases that we want to operate, and the delays between the blanking times, and many other parameters, just all in this symbol interface. And the other interesting aspect of this is that once we've finished with all of our tweaking and all of our modifications, we can save the register map, and then by working with your contact at MPS, we can even develop specific suffixes for your memory. So this programming can already be done from production, and you don't have to worry about programming these ICs in-house. One last challenge that I wanted to mention that we need to face when using constant on time is the DC offset error. As I said before, we're looking at the output voltage, comparing it to a reference voltage, and then once they meet in the comparator, we trigger the one-shot timer, and therefore recharge the output. However, this means that our average output voltage is going to be slightly higher than our reference. In order to resolve this, what we do is we add an error amplifier to the reference voltage. This means that we can reduce our average output voltage to the required or to the desired voltage by reducing the value that we send to the comparator. This eliminates this steady state error in the output voltage, but doesn't affect the ability of the control loop to respond to changes in Vout. So just to recap, we have increased transient performance, much faster transients to be able to deliver the energy to our load. We also simplify the architecture, and we can operate more seamlessly between light load and heavy load. This is good for applications which have, sudden bursts in power requirement. And we've also been able to resolve some of the challenges, such as being able to maintain the stability of the converter, even if we're using capacitors with low ESR. The other aspect is that we can maintain a quasi-stable frequency, so we can have a better idea of the frequency our converter will be operating in steady state. And we also simplify for these very high current applications the development of multi-phase converters by implementing auto-interleaving capabilities in our power modules. So just as a very quick overview of the power modules that we offer for these FPGA core current rails, we have a wide range of output currents going from 10 amps to over 100 amps. They also come in the option of single output, for example, this 10 amp module or the 100 amp module that I showed before. But we also have multiple output versions, such as the 3690 family, which can deliver dual 13 amps, 18 amps, or 25 amps. These are also completely analog. So if they need to operate in an application that doesn't require serial communication, these only require the output, the resistive divider for the output voltage, same as the 3683 family. And then the other ones do have I2C or PM bus capabilities, and the 3698, which is one of our newest modules that can deliver up to 120 amps or an 80 amp and a 40 amp rail, also allows for these high-speed communication protocols that are required in some of the newer higher-end FPGAs. Oh, and this 82504 is our quad output 25 amp module. So the outputs can be joined together as required. So we can have either 425 outputs or 125 amp output and 175 amp output, or whatever is required. This further increases the flexibility and the capability of using the same part for multiple power rails in complex designs. The other aspect that I wanted to mention is our reference designs. So on our webpage, you will be able to find our reference designs for the main FPGA manufacturers, such as AMD Xilinx or Intel, used to be Altera, or Lattice Semiconductor. We have a very wide range of reference designs for most of the commonly used FPGA models, and generally, we have a block diagram that you can use to get a start on your power tree design. And for some, we also have schematics, we have boards, and other information that can be of use when designing your power tree. If you have any questions about any of these, you can also reach out to your local MPS contact, and we'll be happy to clear any doubts up. And finally, I didn't want to finish before giving you a very quick overview of the key advantages of using power modules. As you know, MPS has been delivering power converters, monolithic power converters, so we integrate the control loop and the power FETs in a single package. And now the next step of this integration is to also add some passive elements into the same package. So in our modules, we integrate the converter and the inductor and some of the other passive elements in the circuit, such as the bootstrap capacitor, or such as the decoupling input, some of the decoupling input capacitors as well. This not only reduces the solution size significantly, as you can see in this comparison here, it also greatly simplifies board layout and reduces the amount of iterations on board design. For example, you don't want somebody mistakenly placing the wrong routing in the wrong place and placing a signal that's very sensitive to noise underneath the inductor, and then you need to redo the whole board. This is great. This risk of this is greatly reduced by using our power modules, and also by adding all of these elements into a single package, we reduce the size of the BOM, which also simplifies the manufacturing process and the procurement process as well. And for those of you who work in applications that require a lot of emphasis on EMI, a couple of things to mention is that, for example, for minimizing radiated noise from EMI, this very often comes from, for example, the switch node. By integrating the inductor within the module, we're effectively minimizing the switch node as much as possible, implementing it straight onto the lead frame, and therefore reducing greatly the amount of emissions that come from this. Also, as I said before, we integrate the small input capacitors on some of our modules. This greatly reduces the size of the hot loops, and therefore greatly improves the EMI performance. Most of our module portfolio is designed for industrial applications, but we even have ACQ 100 automotive grade modules in our portfolio as well. And some of our modules come with full qualification as a complete power supply for with Class B emissions. So that is all that I wanted to share with you today. Kelly, we can, I think, open the floor to any questions that there might be.
Great, lots of good info today, Thomas. So I would just remind everyone, if you mouse over the Q&A button in the bottom of the Zoom webinar interface, you can type in your questions. We already have quite a few in there, and one of the ones that I saw buried in there was, is this presentation going to be available? And yes, for all of you attending today, we will send you an email by the end of the week with a link to a video recording of this session, and as well as a PDF of the presentation. So that's coming your way, and you can always find our past webinars at monolithicpower.com/webinars. All right, and we did have a bunch of questions already in here pretty early, Thomas. First one was, I think, right before the Vertex slide came in. What is minimum current flowing if it is COT?
I'm not sure I really understand. For what current? The inductor current.
Yeah, I'm not sure that's all I got in the question.
Can you repeat it, please?
What is minimum current flowing if it is COT?
In the COT control, well, the minimum current we can deliver is very low. I think it's going to be very similar to the peak current mode. It also depends on what because our COT can also operate right. So we implement something also called forced CCM mode. This is what we use to ensure that we have very low ripple even operating at light load. And in this case, in forced CCM mode, the minimum current could be negative because we're operating in forced CCM, so we can go into the negative instantaneous current. However, in normal COT, it's DCM, so it would be well, zero, pretty much zero plus the leakage current.
Okay, and I did, sorry, he added a follow-up to that one of, for example, if a car is in parking mode without operation. So that was kind of a scenario he wanted addressed.
Right. For these sorts of applications that are dependent on the battery, when operating in idle mode, the COT can maintain very high efficiency, as I said. If it depends on, as I said, if we operate in normal COT, we'll have a slightly larger output voltage ripple in this idle mode because we're waiting a long time between pulses. And if we want to maintain a lower ripple, we can implement 4CCM. The efficiency will be lower at light load, but we maintain this this low ripple even at light load. So it's going to depend on what we implement for operating at light load. But COT is definitely something that is definitely recommendable even for these applications where we have periods of idle states in the load.
Great, thank you. Next one was, how is stability guaranteed in a COT control?
Stability is never guaranteed, is it really? But so the way that we, as I mentioned before, avoid the issue of ESR or the lack of ESR affecting our stability is we use this RC circuit. Let me see if I can find the right slide. By using the RC circuit, we generate a slope voltage, and this allows us to not be so much dependent on the ESR ripple for the stability of this converter. Because if the capacitor voltage is the main component of our total output voltage ripple, then we can enter the subharmonic oscillation, which is going to potentially bring us into instability. This is something that was also an issue for peak current mode control when operating in duty cycles above around 50 or 60%, where any variations or any noise can lead to disarray in the control circuitry and generate instability. So the way that we avoid this is by adding this slope voltage to the feedback and maintaining this periodicity dependent on the inductor current.
Great, thank you. Let's see. I do understand that you have an advantage in load increase for fast response, but how does it increase the performance in load release, I believe.
Well, so when there's a load increase, when there's a load increase, we can deliver the power faster to our converter. The problem is if when there is a load decrease, then the output capacitor needs to re-regulate. So the main advantage and the main issue in all of this is when we have that sudden increase in the load requirement. So the main pain point in all of this is that voltage drop when we increase the load current. That's the main aspect that COT aims to improve for these sorts of increase for this sort of applications where we have this step up in current. For the step down in current, I can't really answer right now off the top of my head. I apologize.
Okay, thank you. If fast transient response is requested, why not use hysterical control? And then,
yeah,
advantages of COT compared to hysterical control.
Yes, well, hysterical control is pretty similar to COT. It just uses a compensator. I think, and it's been a while since I took a look at hysterical control, but from the best of my knowledge, constant on time offers more stability in the fact. So hysterical control can be offers less of a stability in the steady state. It's more prone to being jittery. And with the COT and being able to modify the one-shot timer, we can maintain that fixed output voltage and reduce the error in the steady state to make it less dependent on noise in the circuit.
All right, thank you. Next one up was making the converter response faster by eliminating the compensator must be, I guess, in or at the expense of decreasing the power factor and higher THD, isn't it? And then there's a kind of a follow-up of, could you show the input current waveform? Did you get all that one, Thomas?
Yes. I don't have any plots of the input current right now that I can think of. But it's a good question. Can you repeat the first part, please? Because it's the elimination of the compensator affecting the THD, right?
Yeah, so that's pretty much it. Making the converter response faster by eliminating the compensator must be at the expense of decreasing the power factor and higher THD.
I mean, the THD in this sort of application, it's not something it's something I have to ask the team. I can't give you a good answer right now, I'm afraid.
All right, and Riza, if you're still with us, you see Thomas's email address there on the screen right now. I want you to fire him an email and he'll make sure that he shares that out to the team and gets it answered.
Yes, please.
Let's see, next one we got. compliments on your presentation, Thomas. And then I once had issues with a COT control interfering with a fixed current limit. Is there any current limit built in with your devices? Is it adjustable?
So we do have, yes, we have current limit, and it is adjustable depending on the module, depending, and some of them are programmable via the I2C as well. But yes.
Great. Then a pretty specific one about the NPM 3695. What is the inductor inside it? It's probably in the data sheet, isn't it?
The value of the inductor inside is on the datasheet in the block diagram. I can't tell you off the top of my head, but that's available on the datasheet.
Yep. So just go look at the product online, and there'll be a button there to access the data sheet, and I'm sure that will help address your question. Let me get caught up here. Let's see. Is the COT time and then brackets PWM on time adjustable?
In some of our products, yes. What is also adjustable is the off time. So then you can also limit the sort of maximum and minimum frequencies that you want to be able to operate in. This is especially useful for when you want to avoid emitting in certain bands, frequency bands that you want to not go into, for example, for EMI purposes. Yeah, you can modify the on time and the off time. It depends on it's on a module by module or controller by controller basis.
And then another follow-up on the inductor. Are they off-the-shelf discrete inductors? Are they integrated in the PCB? Are they coupled?
So that depends on also on a module by module basis, I'm afraid. But so we use high performance inductors in our modules, and our modules are, so the inductor is placed, well, it depends on the fabrication process, but for example, we do have open frame modules on a PCB. But the ones that I was mentioning today, for example, the 3695-100, those inductors are placed straight onto the lead frame and then molded in the same package. So that's one single block. And then there are other ways of producing these, manufacturing these modules, more advanced methods where you can even place the inductors stacked on top of the die, and then we can further reduce the footprint size, for example.
Great, thank you. All right. So how to determine if the design is stable? Is this only possible via the load step response?
No, it's part of it. We need to test in many different operations to determine the stability. You can also do so, I think it's worth mentioning, not only you can do so testing your design in the lab, and we also offer simulation models for many of our power modules that you can download on the website, or if not, you can ask your local MPS contact, or you can contact MPS Now as well for these simulation models. But yeah, in order to determine the stability, you need to test different operating conditions. There is another point of COT, which is the fact that traditional ways of measuring stability using, a Bode plot and calculating the phase and the gain margin is not so applicable to constant on time, because of the fact that we've eliminated this the linear element to the control, the Bode plot is not going to give us much information, unfortunately. So the way that we want to establish is through stability, is through simulation and then testing it on the board.
Okay, and this one we got step down current is much worse as the energy stored in all inductors goes to the capacitors. Not sure what the question is, but that's the comment. You want to address that?
I think it's regarding what we were talking about before of the increase in the load current and what happens when this load current is reduced.
Great. It's done. If the load current suddenly drops to 0, but the latch is still enforcing the on time, would the V out spike be larger than in conventional current mode control?
Could you repeat the question, please, Kelly?
If the load current suddenly drops to 0, but the latch is still enforcing the on time, would V out spike be larger than in conventional current mode control?
Well, in that scenario, I think that is a risk. However, I'd have to check and take a look at the waveforms. Trying to plot them in my head is a bit tough, I'm afraid. But please get in touch via email and I can get more information later on.
Great. This one's about, do you have PSpice or IBIS model files for simulation?
We use all of our modules are on Simplest Symmetrics, and we can deliver, and those are the ones that we can give to customers.
All right.
You can also download, however, if you don't have a Simplest license, on the MPS website, there's MPS Smart, which is our simulation suite, which is based off Simplest, and you can download that, and that's free of charge.
Great. Next one, by removing the voltage loop compensator, we might have a DC offset in output voltage.
Yes.
How can this offset be corrected?
This offset, we correct it by adding an error amplifier to the reference voltage here. So the reference voltage we have sort of feed forward from the feedback, and it's to do this error amplifier, and therefore we can reduce the reference down to this compensation value here, sort of equivalent to the one we saw before with the peak current mode control. And then so we're reducing effectively the reference voltage and therefore making sure that our output voltage is we eliminate the DC offset, basically.
All right, next one's an EMI. Are there special considerations required to design the EMI input filter compared to a fixed switching frequency design?
Not specifically that I'm aware, but it's something that I'd have to take a deeper look at. It's not something that I've had to work with these types of controllers at the moment.
And again, we switched back to Thomas's email address, so fire away if you've got more questions for him there. Next one, since there is no compensation whether gain and phase margin measure are valid measurement, for stability in COT.
Yeah, that's the thing. So if you try and plot a Bode plot for a converter with COT control, the results are well, you don't get what you expect, and it's because basically you're trying to implement a Bode plot of a comparator instead of the linear controller. So no, unfortunately, we are actually developing a paper, an application note in precisely on this topic because it's something that we've seen a lot with customers, and so it's something that we'll be able to share with all of you soon, hopefully.
Great. Is there a dedicated release date for the NPM 54313?
I'm not aware of that right now. But if I'll ask the team and we can get back to you on it.
Do you think the next one is, do you think the BW can give any indication about the performance of the system with COT, however the switching frequency is not constant?
Can you repeat the first part? Sorry, Kelly.
Do you think that BW can
Okay.
give any indication about the performance of the system with COT?
Yeah. Sure. That's as I said, that's something that where the team is working on ways of analyzing the stability of the constant on time, and so we'll have more details then. Unfortunately, it's not the thing that I'm working on right now. So my information right now is limited. But again, I'll talk to the team and we can get in touch with whoever asked the question.
Great. Hey, we're actually getting towards the end here. Lots of questions today. Regarding power factor and THD question, I think power factor and harmonic distortion are related to AC-DC converter design, whereas the COT power modules are for DC-DC converters. Maybe that's more of a comment than a question. Anything you want to address there?
Yes, no, I was just thinking it's more linked. I was thinking about the THD more linked to the input filter design. But yes, THD generally is a worry in AC/DC power supplies that have to go back to the network. And in this case, we in the systems that we're working with, we would come from more a DC bus that's already been regulated. So these are point of load converters just before the FPGA.
Great. I think, Thomas, that was our final question. So lots of them today. Again, if there were ones that needed follow-up, fire an email off to Thomas. Thanks again for joining us today. That same page, monolithicpower.com/webinars, is also where we'll place up other future upcoming ones, or we'll send out an email. But appreciate you joining us today and taking time out of your busy day.